Welcome to Astronomy 103. In this section, we will discuss cosmology. Let's begin with a discussion of the universe on large scales. When we look at the universe locally, we see a very clumpy universe. There's stars, galaxies, clusters, supercluster filaments, voids. There's basically things where stuff are and things where stuff is not. But if we look on really, really large scales, the universe is more or less uniform, i.e., it looks roughly about the same. This happens on a scale of roughly about 200 megaparsecs, about 600 million light years. At this scale, basically, this galaxy map shows the largest structure known in the universe, the Sloan Great Wall. There it is, the Sloan Great Wall, right? So there's no structure which is about larger about this, which is about 300 megaparsecs or so. Right? Therefore, the universe is homogeneous, right? So any 200 megaparsec block appears as any other 200 megaparsec block. The universe also appears isotropic on these very large scales. Basically, looks the same in all directions. So the cosmological principle is the assumption the universe is isotropic and homogeneous. Homogeny means the universe has no edge. Isotropy means the universe has no center. Let's talk a little about Ober's paradox. The main difference between nighttime and daytime is that it is dark at night. But this is a bit of a mystery why this is so. Because if the universe is infinite and eternal, this cannot be the case. This is known as Ober's paradox. In particular, in every direction, we should see a star. And so basically the universe is eternal and infinite, and if it was infinite and eternal, then we would see an infinite number of stars in any direction we look. So therefore the Earth should be as bright as the surface of a star. This is clearly not true. So either the universe is either not eternal or not infinite. So it turns out the universe is neither eternal nor infinite. The second thing is that let's talk about is Hubble's law. Hubble's law says the galaxy is moving us at a speed given by the velocity is equal to Hubble's constant h times d, the distance. If the galaxies are all moving away from us, then at some very early time, then all the galaxies were right next to each other. So, for instance, imagine we're blowing a balloon. At any point in the balloon, the things as they expand will move away from each other, right? And so basically, at every point, it looks like galaxies were all moving far away from each other, right? And the distance they move is proportional. The speed at which they move away is proportional to the distance that they are apart. This is very much like Hubble's law. So if we extrapolate this expansion backwards in time, then all galaxies are seen to originate from a single point in an event called the Big Bang. So the question might be, where was the Big Bang? Well, it was everywhere, because basically the Big Bang was created space and time. So no matter where we are in the universe, we are measuring the same relation between recessional velocity and distance with the same Hubble constant. Let's talk a little about age of the universe. So several different ways of determining the time which the universe, at least the part that we see, began. We can use Hubble's law and basically run backwards in time and find basically when the galaxies were all right on top of each other. And that roughly happened about 14 billion years ago. Okay, so in particular, if we take the velocity that galaxies have, v is equal to Hubble's constant times d, right? Then how long it takes galaxies to get there? Well, the time is equal to distance divided by velocity, but the velocity is just Hubble's constant times distance, so it's 1 over h0. So if we use Hubble's constant 70 kilometers per megaparsec, we find that time was 14 billion years ago. Right. So the universe is about 14 billion years old. And in fact, the most distant galaxies that we see, the quasars, are around 13 billion years old. The oldest stars that we can find are all younger than about 10 to 13 billion years. Right. So here's one of the most distant galaxies yet detected, a redshift of 8.6 at a distance of 13 billion light years. There it is, this horrible name, UDF J3954 662 84. Right? UDF means the Hubble Ultra Deep Field. So in order to basically get this picture, so there's this galaxy zoomed in, that red thing in the middle, right? This picture is taken part of the Ultra Deep Field. Basically, Hubble stared at a patch of sky for a million seconds, or about 11 days, in order to get this picture. Right. Here's another runner-up. This is a quasar at a redshift of 7.1. This is observed by the Gemini telescope. So there are, to summarize, there are three independent ways of finding the age of the universe, right? And that are the oldest stars and galaxies. First of all, you could date the oldest stars in the universe, which usually is the oldest, which usually means Geiger clusters. And if you basically look at them, then the best estimate is about something around 11 to 12 billion years. The second way you could do is use Hubble's law, and then divide out the distance divided by the velocity, which is Hubble's constant time distance, or 1 over, which gives you the time as 1 over Hubble's constant. That's about 14 billion years. And the final way of finding it is basically to look at the most distant objects in the universe and find they're roughly about 13 billion light years away, which means that the universe is about at least 13 billion years old. So from the redshift, we know how fast galaxies are moving apart, how fast the universe is expanding. That means they're about 14 billion years old. Every point in the universe was concentrated in one point, one really hot, dense point. So we don't know the physics of this infinitely hot, dense point, but we allow this point to expand a little bit, a few microseconds. We can reconstruct the history of the universe at that point. So let's talk about the first 3 minutes. This is a lot of text followed by some pictures. A large part of the way the universe is today is a result of the history during the first few minutes of the Big Bang. Here's a description of the universe. For a small fraction of a second, the temperature is above 1 trillion degrees Kelvin. At these hot temperatures, light is energetic to create pairs of particles and antiparticles, protons and antiprotons, electrons and positrons, for example, and the equal numbers of each. So particles and antiparticles form and annihilate. For instance, you can form pairs, right? So two photons come together, form a pair, or you can basically have these pairs come together and annihilate and give you two photons back. The universe should create equal amounts of matter and antimatter, but we are made of matter. There's a tiny, tiny imperfection in the amount of matter created versus antimatter, and so the universe ended with much more matter than antimatter. Why this occur is still a mystery, but fortunately it did. Otherwise, we have matter and antimatter around the universe. We'll be annihilating each other, and we never form anything useful. Let's talk a little about Big Bang nucleosynthesis. So, from about 2 minutes to 30 minutes from the beginning, the protons and neutrons started to fuse in the same process as the sun. During this time, protons fuse become helium and other stuff. At about 30 minutes, the temperature and density became too low to allow any more fusion. 25% of the hydrogen has been fused in helium, and so the universe today is 25% helium, 75% hydrogen, and close to color composition today. This process is known as Big Bang nucleosynthesis. So let's talk a little about nucleosynthesis. I'm going to talk about the formation of light elements other than hydrogen. So hydrogen, deuterium, which is heavy hydrogen, helium, and lithium. So that's the deuterium is right there. It consists of a proton and neutron. There's helium, 2 protons, 2 neutrons, and there's lithium, 3 protons and 4 neutrons. So to produce deuterium, what has to happen is that 2 protons have to get close together, and then one of these protons basically is energetic enough such that they release a neutrino and a positron, which carries away the positive charge. And these two things are binding together now as a proton-neutron pair. Okay, and this is deuterium. Now the released positron will then basically come out, annihilate with electrons, and basically emit light. So this is what's also called H2. Now what you can do is this deuterium can then basically form a helium. It meets another proton, emits some light. This becomes helium-3. And finally, you might have 2 helium-3 atoms. They might come together. One neutron will move away from the one helium-3, releasing 2 protons, and release basically proton helium-4 and then some energy as well. So as a result of this, there's trace amounts of deuterium and of lithium, right? So this lithium comes from collisions of deuterium of helium that will remain, accounting for the abundance of these light elements that we see today. Because stars are much denser than the early universe than temperature. At this temperature, deuterium quickly collides to form helium, essentially leaving none of it behind but some trace amounts, and lithium is similarly changed to more stable elements. Right? So most of the universe's helium was formed in the Big Bang, not in stars, it turns out. As the universe continues to expand, light and matter that fills it continues to cool. The hot light that fills the universe during the Big Bang still fills the universe, but the temperature now becomes much, much cooler, about 3 degrees Kelvin. This is called the cosmic microwave background or cosmic background radiation. I don't know what happened here. All right, so let's talk about primordial nucleus synthesis, right? So most of helium and nearly all the next two lightest elements were created in the Big Bang. These are lithium and deuterium. Deuterium is hydrogen with extra neutron. These elements heavier than these elements were created in stars, with elements heavier than iron made primarily supernova. Right? The abundance of helium and deuterium predicted in the Big Bang agree with the observed helium in the universe, as long as the density of ordinary matter is not much larger than what it is. That means most of the missing matter cannot be ordinary matter. If it was denser, you produce more helium and less deuterium. That's not what's observed. So, for instance, if you take the amount of so for instance, the amount of deuterium and lithium, right, depends on the amount of normal matter in the universe. So, for instance, if the density of normal matter was much, much higher, so this is the critical density, was what is observed, right? If much more higher, then we would not observe any lithium in the universe, any deuterium in the universe, and we observe a lot more lithium, right? But what we do observe, basically, is this amount of lithium and this amount of deuterium, which falls small back in the middle of basically having a density of normal matter relative to the total density in the universe of roughly about 4% or so. Okay, so this is very strong evidence for something like Big Bang, because this is the only way really to explain both the deuterium abundance and the lithium abundance. It's very hard. You can't make this stuff in stars, basically. So after 1 second of the Big Bang, all the protons and neutrons were made in the universe during a process called baryogenesis. So this is basically uh, where there's some tiny imperfection in the universe which creates more matter than antimatter. Then from 2 to 30 minutes, the universe makes helium, deuterium, and lithium by Big Bang nuclear synthesis. After about 30 minutes, everything is frozen out, and the universe at this point is a bunch of hydrogen, helium, and free electrons. The universe is now a plasma. There are lots of photons in the universe at this point. They bounce off electrons, so the universe is opaque to light at this point. And as the universe continues to expand, it begins to cool. At a time about 40,000 years after the Big Bang, the electrons and protons start to combine to make hydrogen atoms. And suddenly the universe becomes transparent to photons and they stream in all directions. This process is known as recombination. So at this time, the universe is about 4,000 degrees Kelvin, roughly, not surprisingly, very close to the temperature of the sun. The light gets redshifted basically from 4,000 degrees Kelvin to basically what the temperature we see today, which is 3 degrees Kelvin or so. Right? So the universe is not absolutely cold, but has a temperature of 3 degrees Kelvin, which is basically set by the Big Bang. So at 3 degrees Kelvin, the radiation is in the microwave regime, and so this is known as the cosmic microwave background. This was predicted by a guy named Gamow in 1948 as a natural constant of the Big Bang theory, but there was no attempt to measure it or realize it actually could be measured until the early 60s. Right? So when it was discovered in 1965, the discovery was an accident made by Penn Willis at a Bell Labs telescope in Holmdel, New Jersey. So basically, Bell Labs was one of the big telecommunications provider in the United States at the time, and basically they funded a lot of research back then. But they weren't funding research just for science sake. They were actually funding research basically as commercial research. And what they were looking for, what Penn State was looking for, was source of radio noise on Earth and stumbled across radiation which pervades the entire universe. Right? And it's no accident they made the discovery in New Jersey, because in New Jersey is Princeton, New Jersey. And when Penn State was discovered, they actually went over to Princeton, New Jersey, and asked some astronomers. They were like, "What is this thing that they found?" And the astronomers told them, "Well, this is a prediction made by Gamow that there will be this microwave background radiation." And as a result, Penn State Wilson became famous, won the Nobel Prize for the discovery of the cosmic microwave background. The precision measurement of the cosmic background is one of the pillars of modern astronomy and cosmology. Here's a radio antenna that made the discovery. It's just a giant horn, right? The horn collects the radio signals, basically feeds it and sends it into a detector, basically, in this little housing right here. The recent measurements by satellites such as COBE and others reveal a nearly exact symmetry in all directions, and the spectrum that matches the predicted black body spectrum the better from 1 part in 100,000. The best black body in the known universe. Uh, so the cosmic microwave background, the light discovered from the Big Bang, which was predicted 50 years ago, this discovery in 1965 was a key piece of evidence for the Big Bang. The cosmic background has, as predicted, a nearly perfect black body spectrum with a temperature about 3 degrees Kelvin, also predicted by Gamow. Right. So okay, so this is basically saying the same thing again. And there it is. There's a beautiful picture. There it is. A nearly perfect. These are data points, and this is actually theory. It goes right through all those data points. Very, very beautiful. This is Kobe, right? Basically, what they found was that they found imperfections in this at 1 part in 100,000. This was a huge discovery at the time when it was made. Okay. Uh, more in the more recent, about 20 years ago, Boomerang started observing this as well, and they discovered basically that this is not as that the imperfections there have much greater structure, right? Hot spots and cold spots, right? And another one was actually done by WMAP, and now there's yet another telescope, which is the London, which is Planck, right? So basically, everything is done since WMAP essentially confirmed the same thing. There's really nothing new with Planck. Anyway, so this is a very beautiful map. Basically, the cosmic microwave background. You basically see these hot spots and cold spots there, right? And the size of hot spots and cold spots determine how much matter there is in the universe, right? So in particular, it tells you basically what the geometry of the universe is, right? So if the universe is close, then you have larger spots, okay? So on large scale, it's nearly flat. With matter, it would be okay. So so for instance, this is the largest spot. If it's closed like this, if it's open, the spots will be smaller. But it turns out that basically it has to be flat in order to explain. So you have to have a flat universe. The spots are basically about 1 degree or so. Okay, so these hot spots and coolers are much too large for the amount of visible matter, right? But exactly the right side, if dark matter is included, and actually dark energy is needed as well to explain everything. Okay, so there are 3 possibilities that can happen. Let's see, you can have basically positive curvature. This is a closed universe. You have negative curvature, and you guys have basically flat. And then basically, it turns out that the universe is flat. Okay. So so I want to talk a little about evidence of the Big Bang. So the first thing is basically the expansion of the universe. Basically, we see the universe expanding away from us. If you look at all the galaxies are moving basically all away from us at the rate governed by the Hubble's law. Second thing is that we find that there's 3 degrees microwave background radiation. So basically, there's light that pervades the entire universe, right? In fact, if you ask what's most of the energy in the universe, it's actually the cosmic microwave background at 3 degrees Kelvin, not starlight, not galaxies, nothing. It's actually 3 degrees cosmic microwave background, right? So the second major piece of evidence that for the Big Bang, all right? The age coincidence between different methods. Basically, look at the older stars in globular clusters. You measure the age of the universe from expansion, right? Yeah, another basic piece of evidence in support of the Big Bang, right? So, I want to talk a little about cosmic inflation because it explains one major thing, which is why the universe is so flat, right? So, between 10 to the minus 35 seconds, 10 to the minus 32 seconds, we actually don't really know, right? Okay, there was believed a period of extreme expansion, right? Such that the universe grew basically by nearly a factor of 10 to the 50, right? So basically went from 10 to the minus 35 meters up to 10 to 25 meters, right? Okay. So this expansion is known as the epoch of inflation, right? Now, so this is hypothesized, and you could basically get this to happen, right? If you tune things correctly, right? But this solves major problems, basically. So one thing, it solves the horizon problem, okay? Cosmic microwave background rate appears the same in any direction you look, right? So to better than 1 part in 100,000, okay? But at different points in the universe, there hasn't enough time for light to travel from point A to point B, right? Because we're seeing it right now. So these points are not in thermal economy, yet they know about each other. How is that possible? Well, that means that basically at one point, these things had to be far closer than they were now. And in order to make that happen, basically you had to have a time when they were basically right next to each other. And now they're moving much further apart. Another thing is the flatness problem. The universe has to be flat, right? Okay, so right now we observe the universe to be flat. Okay, so that's basically it's actually not shown here. Basically, it should be right about here, open. Okay, actually it's really close to accelerating. But in order for this to be flat now, it had to be stupidly flat in the very beginning. All right. In order to basically be this flat, you have to have some way of explaining why this gets flat. Well, inflation does that for you. Imagine you take a balloon, you blow up an enormous amount. What happens is that at any one point in the balloon, it's going to look pretty flat. Okay. All right. So, what about the future of the universe? It turns out we are now at a point where we can answer some of these questions about what the fate of the universe is going to be. So, to answer this question, it depends on what the makeup of the universe is, and which is how we got started in this journey in the first place. All right. So let's talk about makeup of the universe. Again, we talked about this before. 95% of the universe is dark, 23% is dark matter, and 72 is something we don't know what it is other than something called dark energy. All right. Um, and in order to basically understand why dark energy was had to be there, um, one thing that we did in the late to, late the late 90s and early 2000s was that we started using Type 1a supernova to measure the distance to distant galaxies. Right? Okay, so you can look at basically these plots here, right? So this is basically a local universe, and you look to large and large distances. What happens is that there was great evidence that the universe is actually not decelerating, but actually accelerating, right? So this was the dark energy which was discovered in the late 90s, right? And in order to basically do this, explain this acceleration, you had to have some sort of extra pressure, which basically pushes things apart. And this pressure had to be basically universal, right? And just always there, and it's not related to matter or anything else. And so this was called the dark energy. Another way people call it is the cosmological constant or so, right? And there are several different cosmological constants. It was believed for a really, really long time that the universe followed the purple curve. There was no cosmological constant, but now we know that in fact the universe has to have cosmological constant, right? And because of that, basically, what will happen is that because of this cosmological constant, and in fact the universe is flat, the universe will expand forever, right? So these three people won the Nobel Prize in 2011 for this: Saul Palmer, Brian Schmidt, and Anna Rees, basically for using observations of supernova to just deduce the accelerating universe. Okay. Now let's talk a little about the formation of large-scale structure. How do these giant clusters of galaxies form? Okay, well, in order to basically do this, we have used computer simulations to see how these giant clusters of galaxies, like the Great Wall, basically form from this. So these are basically some snapshots from a simulation. This at early times, and as we go on and later, basically, what happens is that these these initial fluctuations begin to be pulled together by gravity, and as they get pulled by gravity pulls them to be yet stronger and stronger until basically you form these fine filaments and dense clumps where these are we clusters of galaxies, and these filaments would basically be sheets on which galaxies will flow toward the clusters of galaxies. Here's a computer simulation of that same thing. You start with something which is very, very uniform, let gravity take over, wait a while, and eventually at the end of the time, when the redshift equals 0, you form these large filamentary structures in the universe. All right. So the formation of structure occurs because dark matter halos form as small halos form larger halos. These larger halos merge to larger halos. And so this is the same as in galaxies, and so this is called hierarchical structure formation. So formation of structure and the formation of galaxies are driven by the same thing: gravity on dark matter, gravity on matter, and dark matter mainly.